last few problems on this worksheet that we're going to go over are going to be simplifying techniques. And, you know, the word simplifying is one of those things that is a very general term. Sometimes people don't really look very carefully at the instructions. Some people simplify and solve all mean the same things. But, you know, you think about what the word simplify means, we basically make things simpler in some way. Now, I think where it becomes a little bit confusing is for some people, your idea of simpler might not be our idea of simpler. And a lot of it has to do with what you're going to do with it. When you look at part A, you may have to do some complicated work to make this simpler. But basically, you have two fractions that are being subtracted. And when you combine two fractions with addition or subtraction into a single fractions are often easier to work with, especially when you're solving equations or looking for values where that expression is undefined. So what we're going to do in part A is use a common denominator to get these two fractions combined into one. In part B and C, we don't like to have square roots in the denominator. Okay, we would like to have them in the numerator, and I think the origins of that really go back to simplifying and approximating. We generally approximate square roots with decimals, and it's easier to have a decimal in the numerator than it is in the denominator. But, you know, it's also easier to have integer denominators when you need to combine terms together, which is something you might need to do. So, you know, you can spend some time trying to argue why this is actually simpler, but, you know, it's a conventional thing that we do. You're going to see it done. It's going to have purposes to do it. So, you know, you got to kind of get used to it. Now, part D, maybe simplify isn't exactly the best because it's actually, we would break this apart using log properties. And in some ways that can make things simpler, in some ways that could make things different. I was just trying to come up with some general instructions for a bunch of different things, so let's just kind of get into it and see what we can do. In this first one, we're going to need a common denominator, and even though both of these denominators have x's, right, when we look for a common denominator, you're looking for common factors. Right? The x's are part of sums and differences. They're not part of products, so they're not factors. So basically, the common denominator is going to be both of these denominators together. So what you're going to have to do is you're going to have to multiply by an x minus 3 on this denominator of the first term. Right? You can think about parentheses around the x minus 1, and you're going to have to multiply by x minus 1 on the denominator of the second to make the denominators match. Now, the thing with fractions is you can't multiply the denominator by something unless you also multiply the numerator by that same thing, right? Which is really like multiplying by 1. Okay? So we're going to multiply here on top and bottom by whatever factor we needed to make that common denominator. Now, you could always, one of the important things to understand with simplifying is everything you do is undoable. Probably not a real good word, but you can always undo what you did. You should be able, if you wanted to divide these out and get back to what you started with. Right? So, you know, if you're unsure whether or not you can do something, just sort of think about what property you would use to go back to what you started with and see if that makes any sense. Now, what's going to happen is you're going to get one fraction with the common denominator of x minus 3, x minus 1, and on the first term up here, x minus 3 times 1, I'm going to distribute the 1 here, I get x minus 3. Up here, I'm going to distribute the x here, and I'm also going to associate the negative with the whole second fraction with that x. So I'm really going to think about multiplying a negative x through. That's going to give me negative x squared plus x. Okay? So the negative x times x will give me negative x squared. The negative x times the negative 1 turns into plus x. Right? And then this becomes, let's put my chain of equals here, negative x squared plus 2x minus 3 over x minus 3, x minus 1. Okay? Now, to be complete, I need to make sure that this fraction is in lowest terms. Right? So I should think about taking the negative out of here. Right? And then taking a look at whether or not I think this can be factored. Because it's possible that if this could be factored, one of the factors might divide out with one of the original factors we have in the denominator here. But the only way you can multiply to 3 is 1 times 3, and because it's got to be a positive 3, right, this plus here, both of them have to be positive or negative. They would have to add to 2, and they only subtract to 2. So the signs don't really help, but to be complete, you should at least factor that negative out of the top. It'd be easier to work with. And the reason this is considered to be simpler than what we started with is that now if you needed to figure out when this was undefined, you can look at the denominator. When is the whole fraction equal 0, you can look in the numerator and do some things like this. So anytime you see rational expressions being added or subtracted, you can do that this way using a common denominator. Now, I'm actually going to jump to part C. We don't want this square root of 6 in the denominator. Okay? The easiest thing to do when you just have a radical, a square root in the denominator, is to just multiply by itself. A square root of 6 times the square root of 6, you're actually squaring the square root of 6. We know that squaring and square rooting are inverse operations. So they're going to undo each other and give you just 6. But again, whatever you do to the bottom, you got to do to the top. So you're going to get 3 square roots of 6 over 6. Now, because everything's being multiplied here, right, 3 goes into 3 one time, 3 goes into 2 two times, the 3 and the 6 are outside the square root, right? They're being multiplied top and bottom, so you're going to get the square root of 6 over 2. Now again, you might argue this is not really simpler, but if you had to estimate the square root of 6, it's a lot easier to take that decimal and divide it by 2 than to take 3 and try to divide it by square root of 6. And if you had other square roots that you needed to add together, it's easier to have them in the numerator. Okay. Now, if you tried just doing the square root of 6 in part B here, right, and distribute it, right, that would fix this problem. You would get 6, but you would just basically move it over to the other term. So when you have a sum involving a square root or a difference involving a square root, you need to actually make perfect squares, a difference of squares. So think of this as 1 plus square root of 6. We're going to do what's called the conjugate, which would be 1 minus the square root of 6. And this goes back to the principle that a minus b, right, times a plus b is actually a squared minus b squared. Right? The middle terms subtract out, cancel out, however you want to say it. And in this case, you're just going to get a bunch of squares. So whatever was a square root will no longer be a square root. Okay? Now again, whatever you do to the bottom, you're going to have to do to the top. And on the top, we're just going to leave this factored. Right? There's nothing to be gained by distributing that 3. I'm not going to be able to simplify anything. What's going to happen on the bottom is really this is my A and this is my B, this is my A and this is my B, right? I've got an A minus B and an A plus B. So I'm going to get A squared, right, which is in fact 1 squared, which is 1, minus B squared, and the square root of 6 squared is minus 6. Okay? Now 1 minus 6 is negative 5. I'm going to move that negative out front. Or up top so that it gets read first. We don't like to leave negatives in the bottom, right? And this would be your simplified answer. Now again, it may not look any simpler, but again, the same reasons I gave for part C, apply here. This is the conventional way. We generally, at this level, don't leave radicals in the denominator. Okay. Now, in the grand scheme of things, if you get to 3 over square root of 6, you did everything right. Maybe there's an extra point or so to kind of clean it up and put it in a more usable fashion. But the priority should be just kind of getting there and then simplifying later. Now, log properties, right, come from exponential properties. There's a relationship there. The exponentials and logs are inverses. So we know that when we multiply exponentials, we add the exponents, and when we divide exponentials, we subtract the exponents. So if we see division in a log, they must come from subtraction, and if we see multiplication, it must come from addition. When we take an exponential and raise it to a power, we multiply the exponents. So if we see something raised to a power in logs, we can multiply. So we're going to use all those rules sort of backwards, or really inverse. And when you notice here on the outer level, it's really a division. It must mean that it was a subtraction. It must have come from a subtraction. So we can say, take the log of x squared minus the log of x plus 3. Subtracting logs is the same as dividing what's in the logs, right? Because dividing exponentials would involve subtracting the exponents. And remember that logs are exponents, right? Now, there's no addition, no multiplication going on, but there is something being raised to a power. And when you're being raised, an exponential is raised to a power, you can multiply those exponents. So you can multiply this 2, and this 2, kind of comes out front as 2 times log of x minus log of x plus 3. Okay. Now, there are times when you would have started with 2 log x minus log of x plus 3 and want to combine it into a single log. But you may find in calculus, and you will find at certain points in calculus, that it's actually beneficial to take a combined log like this and split it up. So, maybe simplify isn't the best instruction here, but you do need to be able to do this in both directions. Okay. Here's some more simplifying, and these are directly from calculus problems. So, one of the things that I find a lot is students can do the new calculus part of the problem, but then can't clean it up using the algebraic techniques. And, in the first one, you basically have some multiplying things out to do and combining like terms. But because it's so many, and maybe you haven't seen one this big, it's easy to lose track of things. The second one, you have the same thing going on, but you've also got division. So these are very familiar things, or at least they will be familiar by the end of the semester. But since we don't know anything about the calculus now, we're just going to really try to clean up. Now, when you look at this first one, it's pretty clear to distribute the 2. With this first one, you should really be distributing the 6. And I know we usually have, the thing that's being distributed on the left, but multiplication is commutative. The order doesn't matter. So whether it's left or right doesn't matter. You can turn it around and rewrite it with the 6x in front if you want. But ultimately, you're going to have 6x cubed plus 18x plus 2x squared minus 14. Right? And then, we're going to put this into a usable form. Right? We almost always write polynomials from highest degree to lowest. There are cases and certain applications you would want to do that in the reverse, from the lowest exponent up to the highest. And then we try to, factor if we can. Now, we shouldn't expect anything major to factor here, because we should have, if it did, we would have been able to factor it at the beginning. But there is a factor of 2 we could take out, and that might be worth doing, just to kind of keep the rest of this a little bit more manageable. Okay. Now, same idea here in the second one, right? We're going to distribute, but in this second part of the numerator, right, first of all, you have this minus you're going to have to deal with, so you might want to sort of think of this as its own entity. And now you have more distribution to do, right? So multiplying binomials should be a very familiar skill. Some people use FOIL, first, outer, inner, last. Some people use the distributive property. Some people use the box method. However you do it, you got to be able to find a way to rework that consistently. I'm going to do the top here. I get 3x squared plus 15x. And then up here, I'm going to do my first, outer, inner, last. I'm going to do it right above so I can keep track of everything. 6x squared plus 15x minus 2x minus 5. Okay, you're going to combine these like terms, and then you've got this negative sign to deal with. So, depending on how comfortable you feel, I think there's a bit of a balance here to find. Some people, if you just keep copying things down and do one little step at a time, the writing just becomes so tedious that people lose focus, or people just give up. But if you try to do too much at once, then sometimes you make mistakes. And I think what you have to do is find something that works for you. Sometimes you have to remind yourself, just because I'm writing more steps out doesn't mean it's actually harder. It's just a lot more copying. Okay, so I'm going to leave the minus sign here. I'm going to put the 6x squared plus 13x minus 5 here. All of this is over x squared plus 5x over x squared. I think the biggest thing to try to keep in mind is each of these things individually. You've just never had to do them all at once. So sometimes you just have to be a little bit patient with yourself. You have to be a little bit organized on your paper so that you have more work to do, that you leave yourself space to do that work. And now you're going to combine like terms. So I see a 3x squared and a minus 6x squared. That's going to become minus 3x squared. I see a plus 15x and a minus 13x. That's plus 2x, and then there's a plus 5. And then this is going to be over x squared plus 5x quantity squared. And, this certainly is simpler than what we started with. Now, we do have to be a little bit careful, right? We should think about factoring the numerator if we can. Right? and you can actually find two factors of 15 that subtract to negative 2. So this actually can be factored. I'll put the 5 here and the 1 here. We're going to do minus 5 and plus 1. And then there actually is a common x in the beginning that we could have taken out, right? So this would be x squared because of this, right? When you take the x out, it gets squared. And then we would have an x plus 5 squared on the bottom. So this actually can turn into something much more manageable here. And the reason you would want to do that is in case one of these factors happen to divide out. Okay. Now, again, this is sort of best case scenario. I think if you can get yourself to here, you're in pretty good shape. You understand the basics. You're able to manage all the little things going on and get here. Ultimately, you want to be able to clean it up as much as possible so that it's more usable and it'll be easier to move on. Okay, this is getting a little bit long, but I wanted to just kind of keep this stuff all together. Factoring is another type of simplifying. You're going to just spend a lot of time factoring. We use it to set things equal to 0. You want to recognize the common factor of e to the x here. Right, we had one like this earlier, right? And then we want to factor this. This is a quadratic, a trinomial. 2 times 1 is 2, and 2 plus 1 is 3, so we can bring this all the way down to this, and this is a much more usable form than what we started with. It'll be a lot easier to find the zeros. Now you'd basically be looking at them rather than staring at that e to the x original expression. Okay, so it's a lot to cover. We're sort of summarizing a semester or two's worth of basic concepts, and you don't have to know them all right away, but over time you're going to have to sort of build these things back up so they come back to you more quickly. Okay?